Let's start today with a problem. A particle's position on a line is given by the following function. S of t is t to some number d. We don't know that number yet. Minus 11t cubed plus 27t squared. Now d, all we know is it's positive, and it's some parameter to be chosen. Now we have the following information. At time t equals 1, the acceleration of the particle is 0. So that's what we know. That's what we're given. What do we want to do? Determine another time when the acceleration of the particle is 0, and also determine all times t when the particle is at rest. So what does it mean to be at rest? It says not moving left or right. Well, okay, we'll think about what that means. So first off, this tells us information about the acceleration. We're given information about the function, which is the position. How do we go from position to acceleration? Yeah, two derivatives are the second derivative. So we're going to start out by saying, let's just take a derivative. S prime of t, well, I have t to a number. Even though I don't know what that number is, it's still t to a number. So the number comes down, and it becomes one less number in the exponent. How about the next term? What will be the derivative of minus 11t cubed? 33t squared. And, whoops, 33t squared. We subtract. Derivative of 27t squared? 54t. Good. Good. Nice. And second derivative. S double prime of t. Well, the d is a constant, so that stays. Now, how do you take the derivative of t to the power d minus 1? The d minus 1 comes down. So it's the derivative of something to a power. The power comes down. T to 1 less power. Derivative of 33t squared? 66t. And derivative of 54t? 54. So there's our second derivative. Now, what we want to know is when the acceleration is 0. But the thing is, we don't know what d is, and that really seriously affects the answer. So we have to figure that out. So to help us figure this out, what we'll say is, well, let's use our information. At time t equals 1, the acceleration is 0. So we'll have that 0 is what we get when we plug in s double prime at 1. So plug in 1 into the second derivative, we get 0. So if we plug in 1 to the power d minus 2. What is 1 to the power d minus 2? It's 1. Yep. 1 to any number is 1. All right. Then we have minus 66 times 1 plus 54. Now, of course, this can be simplified. D squared minus d. Negative 66 plus 54 together gives us negative 12. So we want to know, when does that equal 0? Well, what should we do? Factor. If it does factor, does it factor? How does it factor? D minus 4, d plus 3. We're looking for two things that multiply together give negative 12. The fact that it's negative means they're going to be different signs. And when we combine them together, we get negative 1. So negative 4 times 3 gives us the negative 12. And you'll see that the minus 4d and the plus 3d combine together to give us just a minus d. So that says, well, d could be two possibilities. D could be 4, or d could be negative 3. But they're not really two possibilities, because what else do we know? Yeah, d is greater than 0. So we can knock that possibility out. So I say, aha, now the good news. We really have what s prime of t is. So I can replace everywhere where I see a d by 4. So it's really 4t cubed minus 33t squared plus 54t. And for s double prime of t, we'll have 4 times 3, which is going to give us 12, t squared minus 66t plus 54. So now we've determined d using our information. So we're ready to start answering the questions. So we want some time when the acceleration is 0. So we set the derivative, second derivative, equal to 0. 0 equals 12t squared minus 66t plus 54. We say, great. We just have to factor that. And we're probably thinking, great. Now we have to factor that. But actually it's not so bad. Notice, what do they have in common? 6. So pull out what they have in common. 2t squared minus 11t plus 9. But there's something else. We already know, beyond a shadow of a doubt, to the core of our very soul, that this factors. And not only do we know that it factors, we know what one of the factors has to be. What's one of the factors and why? T minus 1 has to be a factor because we know when t equals 1, the acceleration is already 0, which means that 1 is a root. So we don't even have to think hard about one of the factors, which is good. That means we only have to think a little bit about the other one. If I need to get it to a 2t squared and I have a t, what do I have to put here? 2t. And then if I have to get to a plus 9, and here's a minus 1, what has to be there? Minus 9. Now, of course, we can double check. 2t squared, then we have minus 9t minus 2t, which is minus 11t, and then a plus 9. So we already knew about the time t equals 1. The other time is going to come from here. When does 2t equal 9? Well, that says t equals 9 halves. So this is when acceleration is going to be 0 at our other time. All right, well, that's something. But the problem said, we want more. This problem is greedy. It wants more. It says, look, all the times when the particle is not moving, it's at rest. So let's rephrase that in terms of our notation here. In terms of s or s prime or s double prime, what is this last thing asking us for? It's talking about s prime, and we want s prime to be 0. So this is secret code. So we're not moving means that our motion is 0. There's no change happening with our motion. So, all right, so we come up to our motion. 4t cubed minus 33t squared plus 54t set equal to 0. Now that's a cubic. That's a little bit harder. But it's not terribly hard to get started. What's something we can do? Yeah, get the t. Pull that out. T times 4t squared minus 33t plus 54 equals 0. Now, what would be amazing? It would be amazing if this factored, right? I'm going to go on faith. I believe in miracles. All right. So let's think. How could it factor? Well, it could think about ways to break 4 apart. And 4 can break apart as 4 and 1 or as 2 and 2. And 54, well, there's a couple ways to break 54 apart. 1 and 54, 2 and 27, 3 and 18. There's a lot of ways, actually. 6 and 9. But I think it's going to be a 4t and a t. That's my guess. And let's see. 54, how does 54 factor? Think. So, wait, what did you say? Minus 9, where? Here? Here? Minus 9, and you said minus 6. Let's see, does that work? 4t squared minus 24t minus 9. Oh my gosh, minus 33t. And plus, our belief has paid off. It factored. Now, if you didn't know how to do that, quadratic equation would work. So, and I will tell you that if you're getting nervous, would we put these kind of numbers on a test to factor? No. Yes? You haven't had any of my tests yet. You don't know what they're like. So, no. We put the bigger numbers on the practice problems. The ones on the test are fun. Okay, so we're ready to read off our answers. So what do we get from that point? 0. Okay, how about from this one? 9/4, because you take the 9 across, divide by 4. And how about this one? 6. So these are the 3 times when the particle is at rest. So there's 3 times when the particle just stops and says, I need a break. At time 0, time 9/4, and at time 6. All right, good. Nice. Fun stuff. All right, well, what's today? Well, we've already mentioned what today is. Today, we're going to add more rules to our list of derivatives. So, what rules are today? And the answer is the trigonometric functions. So the trigonometric functions are really important. And so we're going to start there. Now we need a couple of facts. We need to know a few things that we've already talked about, we've already covered. And so what are they? Well, some basic facts about limits. Because remember, if we're going to take a derivative, we need to use a limit. We always use the limit definition of derivative to establish the rules. So the limit as h goes to 0 of sine of h over h is 1. And we also showed the limit as h goes to 0 of cosine of h minus 1 divided by h is 0. So these are things that we've already done before. Things that we've seen in our past. All right. We're also going to need some trig identities. These are trig identities that you don't need to have memorized, but we can use. If you want to see proofs of these trig identities, if you look at the trig review video on the website, we actually do have a short proof of these. So sine of a plus b, that's sine of a times cosine of b plus sine of b times cosine of a. And cosine of a plus b is cosine a cosine b minus sine a sine b. On a side note, you can get the double angle identities from these. So for example, if a and b are both your angle theta, then you get sine theta cosine theta plus sine theta cosine theta, which is your 2 sine theta cosine theta. And if here a and b are theta, you get cosine theta minus sine theta, which is your cosine squared theta minus sine squared theta. So those double angle identities you should know. You don't need to know these identities here. Now we're going to start by doing the sine function. Now what you see on the very bottom here is you see 2 curves. The top curve is the sine function. And it starts at 0, and then it moves in what you could describe as a sinusoidal pattern, which is basically saying it looks like a sine curve. It goes up and down. Now what's on the bottom? Well, what's on the bottom is we're trying to think about what should the derivative look like. So for instance, at 0, if you were to sketch a tangent line, it would look something roughly like that. And you'd say, okay, well, what's eyeballing? What does it look like? What's the slope? About 1. So we say, okay, so in the derivative, we'd hit about 1. And then we say, okay, if we move along, we'd see, okay, so there's this part right here. Well, what's the slope of that? 0. So if you were to drop down to the derivative, it should be 0. And you can see the slope is plus 1, but then the slope is sort of shallowing as you move up. So the derivative is going down. Now, say we move further along, and so we'll go through a variety of colors here. Suppose I'm over here, and I look at my slope. Well, what is it? It's negative. And it's, it's not hard to tell exactly, but it's, who knows, maybe about negative 1-ish, I don't know. But you can see, I start at positive 1, and my slopes are going down. Now, suppose we move over. All right. Now we're over here. What's happening? What's that slope? 0. So if you go down to your derivative, you'll see you get 0. So you can kind of see that by thinking about the shape of the curve, if you look at the shape of the curve, you can start to extract the shape of the function. If you went one more, because we're only going out little bits and pieces over here, we're back to where we started. So we're seeing that when the sine curve goes through one revolution, it looks like our derivative should start up 1-ish, go down to maybe negative 1-ish, and head back up to 1-ish by the time we end. And then since the sine curve is repeating, this curve, whatever it is, should also be repeating. Should repeat the same frequency. So we think to ourselves, have we ever seen a curve that has this sort of behavior? Because remember, this is the sine curve. What is this? Does this look like anything? The cosine. Oh, that would be amazing, wouldn't it? The derivative of sine were like that would be like, whoa. Like it was meant to be. Like the math gods have smiled on us. Well, the math gods have smiled on us. So the derivative of sine is cosine. All right. So let's prove it. So we do what we always do when we want to take the derivative of a function. We say, okay, what's the rule? So if I want to take the derivative of any function, so in our case it's sine of x, I say the definition for the limit as h goes to 0, I plug in x plus h into my function, so sine of x plus h, and then I subtract off sine of x over h. Now we start thinking about what we want to do. We want to get to a point where we can use our rules for limits, and we're not there yet. So we say, okay, what can we use to rewrite? Anything. Is there anything that we have that can help us rewrite our expression? Yeah, we have that sine of a plus b. So we apply it. So here a is x and b is h. And so we just apply our rule. So it becomes sine of x cosine of h plus sine of h cosine of x minus sine of x over h. And now what we're going to do is we're going to just do a little bit of bookkeeping, move stuff around. But the next step is nothing more than just rearranging. So there are two terms that have sine of x in them upstairs. I pull that sine of x out. There's a cosine of h minus 1, still over h. There's one term that has a cosine of x, and that's a sine h over h. And we can see that these two pieces are pieces which are really nice. And as we take the limit as h goes to 0, the sine of x and the cosine of x, they don't change. So we just need to understand what happens to those two parts. Well, they go to 0 and 1, and therefore we end up with cosine of x. All right. Well, that was nice. So the derivative of sine is cosine. But you know, we should do the flip side. How about the derivative of cosine? What should that be? Wouldn't it be cool if it were like sine? Wouldn't it be like, yeah, that would be like really convenient and easy. Well, no, we can't have everything be convenient and easy. So the derivative of cosine is negative sine. Okay. So what's the proof? The proof is the same. Start by saying we take the definition of the derivative, so we plug in x plus h. We apply the rule for cosine, and the rule for cosine is different. So it's cosine x, cosine h, minus sine x, sine of h. Now, that's the only step that's different. Everything else we do is the exact same. So, for example, here we're going to put the cosine x's are going to come together, and that'll end up with giving us a cosine of h minus 1 over h. The sine of x will have a sine h over h, and then you have that minus sign. As before, the cosine h minus 1 over h goes to 0, the sine h over h goes to 1, and so we get our result. Now, if you look at the curves, you can actually check and see that it makes sense that this is the case. So what's happening here is the top curve, now this top curve is cosine of x. The bottom curve is the derivative of cosine of x. And so what you can check is you sort of eyeball a couple things. Okay, initially, at the start, we should be 0. Okay, we are. Then if you look over here at the next point, over a little bit, so this would be at pi halves. That's when the cosine is at 0. What's your slope? It's going down, so it's negative. So that's why you have that sort of, it's not sine of x, it's that negative sine x, because your slope is going in a slightly different way. And of course, you can keep going. You go over a little bit here. This would be at pi. We see we have a 0 slope. Here would be at 3 pi halves. We have a positive slope, and so forth, and so on. All right. So the derivative of sine, positive cosine, derivative of cosine is negative sine. I wish there was like a nice convenient way to remember this, just practice, and you'll get better. In a few weeks, as we get really close to the end of the class in Calc 1, we're going to talk about what are called antiderivatives, and then we're really going to throw off the confusion. Or I shouldn't say throw off, we're going to layer it on. So be careful, be careful. Okay, so let's just check a couple things, make sure we know how to do it. So we're going to take some derivatives. So our original function is sine of x. So I want to find these various pieces. So dy dx stands for the derivative of sine? Cosine. All right. So d2y dx squared, what does that mean? Second derivative, and we're going to end up with negative sine. Because we have it right here. Derivative of cosine is negative sine. So this says take the derivative of the derivative, so you come up to the previous line. The d3y dx cubed, which derivative is this? Third derivative. What does that turn out to be? Negative cosine. And the way you get the third derivative is you go to the second derivative and you say, what's the derivative there? In that case, you say, look, the negative is a constant, so you take that constant times the derivative of sine. All right. What about d4y? What will that be? That's the fourth derivative. That turns out to be sine. d5y, the fifth derivative over dx to the fifth, is cosine. Now, we could keep going because eventually we need to get down to the 107th derivative. Now, there's not a lot of space here, so I can't imagine in the dot, 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 we're going to be able to put in all the intermittent 101 derivatives that are missing. But what do we see? Someone mentioned the word pattern. What's the pattern? Yeah. Notice it's going through length 4. Sine, cosine, negative cosine, sine again. So when you hit that fourth derivative, it's like you've reset. So as an example, the fifth derivative matches with the first derivative. So we could think and say to ourselves, oh, like so every 4 derivatives we are restarting. So let's think about the number 107. Well, what's true about 107? Well, one thing that's true, it's 104 plus 3. And you're probably thinking, well, that's true. It's also 105 plus 2, Steve. But what's special about 104? Yeah, see, this is a multiple of 4. It turns out to be 4 times 26. So what happens is we're going to take a bunch of derivatives, but remember, every time we go through a step of 4, we're back to where we started. So we're going to go through 26 cycles, and then 3 more. So if we're back where we started, so the 104th derivative will be here, back to sine. Then we just keep going. 105th, 106th, 107th. Negative cosine x. So in other words, it's the same as the third derivative. So we like the derivatives of sine and cosine because they repeat themselves. One of the things I should say about sine and cosine is these are very important functions in mathematics because sine and cosine are what we call periodic functions. They repeat themselves after a certain length of time. And periodic functions are very important because a lot of things that happen are modeled by periodic things. So for example, if you look at the sunrise and the sunset, that's periodic. It's very predictable. Tides coming in and out are periodic. Lots of natural behavior happens to be something which falls on a somewhat periodic basis. So these are going to be important functions, especially when you start getting into modeling real-world phenomenon and, of course, differential equations, which is a great class. Well, let's do some more practice. All right. So we want to take the derivative of sine of 2x. Now, I know some of you are like, I know how to take that derivative, mwahaha, but we don't know the really cool way to do it yet. So let's think about how we could do it. What we do know is we know how to take the derivative of sine and cosine. So I can say, instead of taking the derivative of sine of 2x, I'll take derivative of 2 sine x cosine x, because these are equivalent expressions. So the derivative of sine of 2x is equal to the derivative of 2 sine x cosine of x. All right. The nice thing is we do know how to take derivatives of sine and cosine, and we know how to take the derivative of a product of sine and cosine because we have a rule, which is the product rule. So, the product rule. It'll be 2 times the derivative of sine, which is cosine, times cosine. So I took the constant, just stays as the constant, derivative of the first times the second, plus 2. Now I leave the sine alone, and then I times it by the derivative of cosine, which is negative sine. All right. Now that is the derivative. We could justifiably stop there. But I don't think we get the great aha moment. We're like, I guess, okay. We want that great, well, isn't that an interesting thing? Okay, let's get to that moment. What do these have in common? Yeah, they have a 2 in common. And then if we factor it out, cosine times cosine is cosine squared x. And now there's that minus sine squared of x. Now cosine squared x plus sine squared x we really like. It's super nice. Cosine squared x minus sine squared x is not too bad either. What does this turn out to be? It's a double angle. That's cosine 2x. So we've got 2 cosine 2x. So isn't this interesting? See, we get that the derivative of sine of x just by itself is cosine of x, and the derivative of sine of 2x is 2 cosine 2x. That's an interesting pattern. It kind of vaguely reminds us, we've actually did previously that we saw, hey, look, the derivative of e to the x, that's e to the x. And then we said the derivative of e to the 2x, do you remember what that was? 2e to the 2x. Oh, my goodness. I suspect there's something going on here. I'm very suspicious. I wonder what it could be. Well, we'll figure that out, I think, in the near future. Find the derivative of x squared sine of x plus 2x cosine of x minus 2 times sine of x. So, well, we're going to have to be patient here. What's the derivative of x squared sine of x? What rule do we need? Product rule. Okay, so let's just start. I like to do the derivative of the first. So derivative of x squared, 2x. And the sine x, what do we do? We leave the sine of x alone. It will get its chance. Don't worry. Every term gets its chance. Next, the x squared times the derivative of sine, which is cosine. Okay, now we go to our second term. What rule do you need here? More product rule. That's cool. Lots of product. We're going to be very productive today. Okay, derivative of 2x, 2. And the cosine x we leave alone. Plus 2x times the derivative of cosine x, which is negative sine x. All right? And the derivative of negative 2 sine x? Negative 2 is a constant, so we just start by writing down negative 2. Derivative of sine is cosine. All right. Now, again, we could say we're done, but we suspect that something nice might be happening here. We've lived a good life. Something beautiful might be about to happen. Do we see anything happening here? Okay, someone said the 2x sine of x's, they actually cancel because there's a minus attached to this one, but not to that one. So those cancel. Anything else? The 2 cosine x, again, there's a minus attached to this one, but not to the other one. And of course, the x squared cosine x is x squared cosine x. Well, that's remarkable. So we had something which is a very large expression when we took its derivative, it collapsed down. So that's fun. Now, something to look forward to next semester when you're doing Calculus Part 2, the return of everything. What you see in Calculus Part 2 is you, instead of starting here and going there, you start here and go there. So it's going to go backwards. That's the fun stuff. Good times, good times. All right. Well, we've done some trigonometric functions. Are there any left? Oh yeah, there's more. That's the nice thing about trigonometry. There's always another identity. There's always another trig function. All right. Okay. So, for the other trigonometric functions, we can use our fun facts. Okay, so we don't want to keep going back to limits. Our goal is use limits as much as possible. So we're going to be in that mindset, I don't want to use limits if I can avoid it. The good news is once you have sine and cosine, everything else, as far as trigonometry is concerned, is some combination of sine and cosine. So let's start with tangent. How can I write tangent in terms of sine and cosine? It's sine over cosine. So if I want to take the derivative of tangent, I'm going to take the derivative of sine over cosine. What rule applies? Quotient rule. So you apply the quotient rule. You take the bottom, which is cosine, times the derivative of the top, which is cosine, minus the top, which is sine, times the derivative of the bottom, which is negative sine, all over the bottom term squared. Now upstairs you'll see cosine squared x plus sine squared x. What does that become? It becomes 1. So you get 1 over cosine squared x, which is known as secant squared x. All right. Now since we're talking about tangent, let's do the cotangent. How do you find cotangent? It's cosine over sine. For cotangent, very similar process. The only thing that happens is you end up getting a negative in the exponent. And downstairs it's a sine squared. So it's negative cosecant squared. Now, because we greatly prefer things without negatives, I will tell you that the one of these that you should memorize is the tangent one. The cotangent one, if you have a few extra brain cells, and you're young, you have a couple of extra brain cells left you can memorize. But if you must memorize only one, definitely memorize the tangent one. Okay, are we done with our trig functions? No. No, came the excited. What's a good one? What's another one? Secant. Okay, how do you write secant? 1 over cosine. Okay, do we have a rule for 1 over cosine? Yeah. You can use the quotient rule again, or you can say the reciprocal rule, which is really a sort of a special case. So the quotient rule says you take negative the derivative downstairs. So the derivative of cosine is negative sine. So it's negative of negative sine. That's your numerator. Then you square your denominator. Now what you end up with is sine x over cosine squared x. We want to rewrite that. So how can we do that? So someone said, hey, there's like a tangent and a secant floating around. What you can do is you can say, well, look, I have a single sine and I have 2 cosines. So I'm going to pair up one sine with one cosine. That would be sine over cosine, which is tangent. Then I'm left with a 1 over cosine, which would be a secant. And therefore, the derivative of secant is secant times tangent. Now the last one, do you remember what the last trig function will be? Cosecant. It's same process. And lo and behold, you get minus cosecant cotangent. So those are your various trigonometric functions, or at least the other ones. Now you'll notice I wrote the tangent and secant down here, and I put a box around them, because those are the ones you want to remember. These are the ones that are going to be used more often. Now it's not because tangent is somehow an inherently better function. I honestly, truly believe that it's primarily because the derivative of tangent does not have a negative coming in, where the derivative of cotangent does. That's the big difference. That's the big difference. All right. Okay, how are we doing on time? We probably have plenty of time. Plenty of time. Plenty of time. All right. Let's see. So let's do some examples. Probably going to regret this example, but we'll see where we go. Find, and what does this notation here mean? Third derivative with respect to theta. We're thinking of theta as our variable of tangent theta. All right. So we're taking the third derivative of the tangent. Well, if we're going to take the third derivative, we should probably start by taking just plain old derivative. So here, I'll just call f of theta to be tangent of theta. So I'm after the third derivative. Do we know the first derivative? Derivative of tangent? Secant squared of theta. Because we're going to keep our variable here as theta. Now, how do we take the second derivative? Well, what's another way to think of secant squared theta? Secant times secant. So, if we take it this way, well, the derivative of secant is secant times tangent, or tangent times secant, in some order, times secant, plus secant times the derivative of secant, which is secant times tangent. Which becomes, well, these are the exact same, so there's two of them. Each term has two secants, so that's a secant squared, and then there's a tangent. So 2 secant squared theta, tangent theta. All right. Now, we want to go do one more. Why? Because what derivative are we after? The third derivative. Triple prime. All right. So, product rule. 2 times derivative of secant squared. Do we know the derivative of secant squared? Yeah, it's this thing. That's the derivative of secant squared. We just did it. I'm not redoing it. I'm not crazy. I recycle. I'm a green mathematician. Okay, so 2 times derivative of secant squared times tangent plus 2 secant squared times the derivative of tangent. Derivative of tangent is secant squared. So what you end up with is you end up with 4 secant squared theta, tangent squared theta, plus 2 secant to the 4th theta. And there you go. All right, that wasn't so bad. Now let's do the other one. So for the other one, we'll think of our function here as being secant theta. We don't have to go quite so far. What's the first derivative turn out to be? Secant times tangent. Okay, so the second derivative, what rule do we need? Product rule, because there's two things multiplying. Derivative of secant. So yeah, secant times tangent. Then we're going to multiply it by tangent, so derivative of the first times the second, plus secant times the derivative of tangent, which is secant squared. So we end up with secant theta, tangent squared theta, plus secant cubed theta. In general, it turns out that if you're taking derivatives of secants and tangents, you always end up with some combinations of secants and tangents. All right. Find the tangent line to the curve y equals 6 times tangent of x minus root 2 secant of x at x equals pi fourths. All right, this is a good question because it says find a tangent line of a function. We can always do that, even if our function has trigonometric terms involved. So if I need a tangent line, what information do I need? Slope and point. Remember, we need both. We don't have a full point yet because this is an x-coordinate, so I need a y-coordinate. So let's get our point. So our point will be at pi fourths, comma, and then we plug pi fourths in. So 6 times tangent of pi fourths minus root 2 times secant of pi fourths. And you're probably thinking, great, let's leave it like that. But I think we can go further. For example, tangent of pi fourths. What does that turn out to be? That turns out to be 1. Secant of pi fourths. Do you know that one? So that one may not be as quite as familiar, but let's think about secant. What is secant related to? It's cosine. It's 1 over cosine. How about cosine of pi fourths? You know that? Root 2 over 2. You can also write cosine of pi fourths as 1 divided by square root of 2. So if you flip that, secant of pi fourths is square root of 2. So pi fourths, 6 minus 2. Pi fourths, comma 4. That's a reasonable point. Now the slope, what will we need? We'll need the derivative. So let's take our derivative. Y prime. Derivative of 6 times tangent of x. 6 secant squared x. Okay, minus root 2. Derivative of secant. Secant times tangent. I should keep saying secant of x, tangent of x. All right, now is this our slope? No, not yet. It's our derivative. Now our derivative won't be a slope until we evaluate. What our derivative is, it's a function that gives our slope at any given point, but you have to evaluate to actually get the slope. So we now plug in pi fourths. So at pi fourths, well, we're going to get 6 times secant of pi fourths squared minus square root of 2 times secant of pi fourths tangent of pi fourths. But the good news is we know these numbers. Secant of pi fourths is root 2. Root 2 squared will be 2. 6 times 2 makes the first term 12. And I have a root 2 from the secant of pi fourths, a 1 from the tangent of pi fourths. Root 2 times 1 gives 2. So 12 minus 2 gives 10. So there's our slope. Our point, pi fourths 4, our slope 10. So we're now ready to say our line is y minus our y coordinate, which is 4, is equal to our slope 10 times x minus our x coordinate, pi fourths. And that is a perfectly fine way to leave our answer. All right. So, I want to stop after our next thing. So the motion of a spring. And there's something that you'll hear about in physics called Hooke's law. And Hooke's law says that if you have a spring, so if you're not familiar with what a spring looks like, think about it as a slinky. So here's a spring, and on the end there's usually like some sort of weight attached to it. And what happens is if you pull a spring, so if I take the spring and I were to pull it down, the spring would try to pull it back up. So in other words, if this is its natural state, if I pull down, the spring says, no, go back up. Similarly, if I tried to push up, then the spring would push against and say, hey, you need to go back down. So if you think about what's happening, you can think about it as the acceleration, which really means a force here. It depends on where you're at. So displacement is just a fancy way to say location. So if you pull down, it's trying to pull you back up. If you push up, it's trying to pull you back down. So the nice thing is that a spring really wants to be balanced. It wants to get into an equilibrium. Well, so how do you actually go from an equation and say, hey, I'm looking for something where the second derivative is somehow some constant of of the function itself. So s double prime equals minus ks. The answer is you take differential equations because they love these kinds of things. You're going to go crazy about this in like week 2 of differential equations. You're going to have lots of fun. Now for us, it just suffices to say you can solve it, And it turns out that the type of function that solves it are the sine function or the cosine function. And in general, you get that the solution looks like a times sine of root k times t plus b. Now, it's very easy to verify it if you take the derivative. We don't have the tools yet to go all the way through, but it turns out to be true. Now, if you think about what's happening here, essentially what it says is that the second derivative is the opposite sign of location. So if you come here, this is a really crowded picture, but here on the blue, that's the sine function. So you can think of it as you have a spring, and this is how the spring is behaving. It's going up and down as you march forward in time. In the red, that's the first derivative, so that tells you velocity. But at the very bottom is the green. That tells you acceleration. So if you look at how the position relates to acceleration, you can see it has this property, that they're exactly opposite, that they march opposite to each other, so that it has this beautiful property. So somehow this relationship that says, lo and behold, I'm exactly opposite to my acceleration, things happen. Well, something else can happen, which is you can have what's called the damped motion. So there's this theory that says if I have a spring and I release it, it'll just keep going up and down and up and down and up and down, because of course in physics you always start to say, look, there's nothing else acting on it, it's a perfect world, there's no friction, there's no gravity, make lots of other assumptions. But oftentimes there's something called the damped motion. And what happens with the damped motion is that something is causing it to slow down. So what you have is over time, you get smaller and smaller variations and things disappear. So I claim this is an example of something which would have a damped motion. Now the sine of t, you should think of it as saying that's causing it to go up and down. So sine of t looks roughly like this. When I multiply sine of t by something like e to the negative t, what's happening is I'm applying this e to the negative t. So I draw the e to the negative t, and I draw it on both sides. And what the sine does is it goes in between these. And so you can see what happens is it's still going up and down, but it starts going up and down at lower and lower heights. So what happens to the acceleration? Well, so that says take the derivatives. So in the interest of time, I'm going to try to go through these derivatives really quickly. But there's nothing very surprising here. So you take the first derivative by the product rule, derivative of the first times the second, plus the first times the derivative of the second. And if you take the second derivative, well, you'll get e to the minus t, sine of t, then you're going to get minus e to the minus t times cosine of t. And then here you're going to get a plus, actually a minus e to the minus t times cosine t, and a minus e to the minus t times sine of t. And these two cancel, and you end up with a minus 2 e to the minus t cosine t. The important thing is, look at this, s double prime versus s. They're not exactly opposite each other. They're out of sync. And that's what's causing the spring to slow down. So if you were to graph something, here's an example, you can see that the motion is the blue, the acceleration is the green. They're not in sync, and that causes it to slow down. You'll do this a lot more when you take differential equations. All right. See you next time.